Okay, everybody, I think we're going to get started. So we're on day 2 from NAND to Lambda. So brief recap of last session. We went through all of the Boolean combinatory circuits. And so now we're going to take one step closer to actually doing some real computing. And so the goal for today is to run through the arithmetic combinatory circuits that we're going to need. And that's going to start with addition. And then we're going to demonstrate how from there we can get to all of the arithmetic computations that we need, building the arithmetic logic unit. And so we're going to start with just some pretty basic Boolean addition, binary addition. And so if you take a look at this, you can see that this is the desired result for our half adder. And our half adder is a circuit or a function which will take 2 bits and return 2 bits. So for Haskell, this will be a tuple. And in the HDL, it'll just be 2 different outs. And so what we want is if we pass in a 1 and a 1, that the result will be 0 sort of in the sum spot and then 1 in the carry. For all other instances, we would like to have zeros in the carry. And then if we are given a 1 and a 0 or a 0 and 1, we want to have this to be a 1 in the sum. And so the idea here being that 0 plus 0 in binary will be 0. 0 plus 1 will be 1 in binary. And then 1 plus 0 will be 1. And then 1 plus 1 will be 0. And we carry the 1 to the next binary digit. OK? So once we establish that, we're going to move on to a full adder. And this is very similar to our half adder, but it involves one additional input. So the full adder needs to basically do the 2 binary digits in its case, but it also needs to handle the carry from the previous operation. So here we have 0, 0, 0, be 0 and 0, 1, 0, 0, 1 and 0, 1, 1, 0, 0 and 1, and then all ones is all ones. So with both of these, you can treat these just as the truth table for just like when we were solving for the Boolean logic yesterday. So we also want to introduce monoids with this today. And so we've talked about them a few times before in other presentations, but I just want to really boil it down to a monoid is an algebraic structure with an associative binary operation and an identity element. And so if we take a look at OR, which we did yesterday, I'm going to go ahead and just demonstrate here real quickly how we might do this. So let's go ahead and we're going to do a new. Can you all see that okay? Should probably get bigger. Bigger? Is that good?
That's good.
Okay. If you don't say stop, I'm just going to keep going, and then it's not going to be my fault. OK, so we're going to have this voltage or where. And for now, there's a few different ways you can do this, but I'm just going to stay consistent with the data declarations that we've already seen. So I'm going to create a new data. It's going to be a voltage or of A is going to be, or actually, let's see if this can build. OK, and then what we can do is we can do instance monoid voltage or where, and we're going to need two things. The first thing that we're going to need is our empty. And our empty is going to be, what's the empty value for or? It's the, first, what's the empty value do? It always returns the other thing, right? So with an or, if you get a low and a high, what will you get? Or low, high? High. And so, and or low, low. So low can be our empty. I think I'm doing that right. And then we're also going to need mapend. And mapend is going to take in two of these, right? And then we're going to return a single one. And here, actually what I'm going to do, I think this should work, is if we, I'm going to import combinatory Boolean. And then we can do uh-oh. I got my syntax messed up. Okay. Oh. I think I got it. Whew. It's always a little bit. Actually, you know what? Live coding is terrifying, but I think that live coding in Haskell is in some ways like the other live coding that I do a lot of is in JavaScript, and it's like at least this told me what I did wrong, right? It's like when it stops working in JavaScript, I'm just like, okay, y'all, we're all in this together. Like, help me out, right? Okay, so now that we've got that, we can actually take a voltage or low. Here, let's boom. Okay, we've got that. So what we should be able to do right now is we should be able to use that mapend as a consistent API and understand that when we use the voltage or, the mapend will give us the high and low. And as you saw in Julie's talk yesterday, we can do this. No, I think we can import data.monoid, and then we can use that that infix operator, and it's just an alias for mapend. Okay, questions about how that worked? Feeling pretty good? Yeah.
What does the A do in the data vector?
Yeah. Yeah. So what the A indicates that voltage or is a higher kinded type, so it's going to take a voltage, and over here, so in the type constructor, the A stays polymorphic. And then here in the data constructor, we constrain it to say voltage or is actually only going to take a voltage. And then same thing here. Those are some of the errors that I was making as I was typing it out. I was forgetting which parts the type needs to remain polymorphic and which parts it gets to be constrained. So
the issue is that.
But why do we even need it if it's on the right side?
Yeah, I think the problem is that those are different things on the left and the right side. You can name it differently.
Yeah, that should be enough, right?
Okay.
That would be, I think, more straightforward.
Yeah, I think I was thinking in the back of my head of maybe like eventually going to functor with this, at which point it would need the A, I think, perhaps. But at any rate, this works. But so does that. So we'll have to we'll have to investigate further. Other questions? Let's make sure this still works as expected. Cool.
So,
yeah.
For me at least, the A is not useful because the only constructor that you have always gives
Takes the voltage. Yeah.
It, so
You might.
you lose the polymorphism.
Yeah. I think that makes sense. Okay, so that's an example of more OR. And so now, what if we want to do? What if we wanted to sort of do some kind of sum, right? So I'm not going to do the binary one because that's going to be up for the exercise. But if we do like voltage int sum, we can say this is going to be voltage int sum of voltage. Here, actually, we'll just do with numbers. So we can do the same thing here. Boom. And so now from here, we can do my sum 1, my sum 2, and get a 3, right? And so the rules for this are that the mempty has to be like the mirror element, right? No matter what goes, whenever the append is used with the mempty, it will return the other argument. So I kind of think of that as the mempty is the mirror. Whenever you look into the mempty, you just see yourself coming back. And then the append has to be associative, right? Not commutative, but associative. And so long as you obey those two rules, you can have monoids. And so here's the question. NAND. We made such a big deal about NAND, right? Can we make a monoid out of NAND? No. And why can't we? There's no identity. And there's one other thing, that it's we can't even make a semigroup of NAND because it's actually not associative. And that's actually one of the reasons why it's one of these universal Boolean operators, is because since it's not associative, we can actually get more things out of it by rearranging the orders that we do the arguments of. And this kind of brought up a point that it comes up a few times in Haskell book as the type classes are being brought up, that we tend to think of like all these things like the monoids to functors to applicative to monoid as getting like more and more and more and more powerful, or like more and more mystical as you go on. But actually the more of these laws that we apply to these type classes, the more constraints we have, which is kind of cool when you think about how all the dangerous things that we do in programming in Haskell are relegated to these like very tightly constrained type classes. Like the monoid has specific laws that it has to obey, right? And that's where we do all of our I/O and our side effecty stuff. And I think that's kind of a cool way to think about it, that the more dangerous a thing is, the more laws in Haskell we slap on top of it to make sure that it stays in line. But it also means that some of these basic like operations, logical operations, don't necessarily fit into that paradigm, right? And so it kind of cuts a couple ways. Okay, so now exercises are going to be implement the half adder, the full adder, and then an add 16. The add 16 will take two 16-bit voltages and return a single one. And increment 16 will take a single 16-bit voltage and then just add 1 to it. And so I'm going to go ahead and I'm going to just run back here so that we have the truth table for half adder up. And so let's start with that. And then once y'all start getting ready for the full adder, maybe it's even possible to the truth tables for these should be in the HDL as well, but I'll go ahead and here, you're not the boss of me. Yeah, you can. They have it like set up so that you can control it from your phone and stuff. It's pretty fancy, but it's not fancy enough that I can't defeat it with screenshots. Remember, when they go high tech, you go low tech. That's why. Okay, so we've got the truth tables up there. Let's get started. And also, this is a good opportunity if you have any questions from yesterday that we can go over. One thing that we're still trying to figure out, or that I'm trying to figure out, is so the data type that for the voltage 16 that I implemented it's very straightforward, but it just takes the 16 voltages. But I'd really like to figure out a way that you could take a list of voltage and fold over it, applying each voltage to the constructor one by one to end up with a voltage 16 at the end. So far, we've had a few attempts but been unsuccessful because the folding function changes its signature with each time.
Exactly. So we were trying to do the same thing.
Yeah.
Looking for the apply function from closure.
Yeah.
Yeah, but I think it's impossible because it won't type check.
Yeah.
I mean, this is like a static thing that, if it was 15, for example,
Yeah.
you would have to get 15 things in an array, and
Yeah.
it's dynamic.
Like we could do, like I wonder, like if there was only 3, we could do something maybe like lift A3 with applicative into it.
Yeah.
But since we have 16, it's not very.
Like we've seen this uncurry thing, which one is uncurry n.
Oh, uncurry?
Like, up to 32.
Oh yeah.
It would have to be a tuple, which is achievable.
Yeah.
And we could go this way.
Yeah.
And you can see, if you look at the definition of those, it's actually 32 functions.
Yeah, it's somebody else did all the writing.
But yeah, that's the way you can do it.
Cool.
And it's static. I think that's the main thing. That type checker. Type checker doesn't work on the while the program is running.
Yeah.
That's imperative.
Yeah.
So that's why it's not doable with arrays. And tuple is static. But tuple, you have to create a tuple, so it has to be 16 and not long.
I feel like there's got to be a way to take like a list of 6 things and then create a function, like create a lambda that accepts 6 things, or like, I don't know.
Tuple.
Yeah, tuple.
Tuple.
Yeah. Yeah, get the length of the list and then make a tuple. Yeah.
Sorry.
Dreams crushed, day 2. It's perfect because we can have an arc and dreams can be restored later on in the week. Oh, also, so once we get these arithmetic circuits figured out, there's a couple different directions that we can go. So we can go into using the state monad to model the data flip-flops and memory registers and RAM. Or we can go into parser combinators to parse assembly to machine code. And so if either of those sound more interesting to you than the other, chime in or ping me on the Discord channel that we have now. And also if you have suggestions in general about how the workshops are going, let me know. I'm always interested in improving.
Indicate that it's like your own function, right? Or but you can't just form can I ask you this? I'm not sure if I'm implementing this correctly. Like, can I use this like ordinary type pattern matching like that with the half adder? Just do like that.
You can, but
it's not perfect, I know that.
Yeah, the goal for all of these is to only build them up with NAND. We had to use pattern matching because it didn't exist. So this is totally valid, but the true intention of the exercise is to express this truth table with the Boolean stuff that we built yesterday.
So I was not here before.
Oh yeah.
I'm now implementing this thing, like trying to get to it.
Sure.
But is this the you probably like transform it into.
And so yeah. So the is this regular Vim bindings? Okay.
Yes.
So the goal is here. So if we do oh yeah, let's get you cloning the. Can you go to GitLab? .com/users/panic later.
Panic later like this.
Perfect. And then if you click on NAND to Lambda workshop, if you can clone this one. Perfect.
But hey, I can do something. I think this is going to be better using the actually get the
Sorry, my eyes are as good. Half adder. Yes, like it's.
I have a typo, but you know what I mean.
Yeah, I think that's going to get you pretty close, but you're going to need, I think. So the half adder will.
So this is what I should be working.
Yeah, and so let me give you a little bit. So if you go ahead and
where are the operators in the
so go ahead,
combinatorial?
Boolean. So these are, this is what we did yesterday.
They need to be full deep.
Yeah, and so kind of I'll do a couple of these. But so with NAND, we use the regular pattern matching. So we say high equals low, and anything else, equals high. And then from there, the goal is to only use the Boolean operators that we have and build them up. So not takes in like an x and returns NAND x and x. Right. And so then from there, it's try to do AND with this and OR with this. And
What's mux and demux? I don't know.
yeah. So mux is a multiplexer. So mux returns this one if this is false, and this one if this is true.
It's like an if.
Yeah, exactly. And then demux goes the other way. The other thing that we did, so these are documented in
I really don't get it. I mean, even the meaning of these operands is not really clear.
So
So-
for that one, the sum is like the half adder is like a pair where the first thing is the exclusive OR and the second the AND. No?
Exactly. So there's also, the idea is to implement them both in Haskell and in the hardware description language. And the hardware description language ones have the documentation for every one. And the way these work is the chip has a name, and then the ins are like the wires coming in, and the out is the wires coming out. And so then here you can use any chips that exist already. So you can do like
A chip is like a circuit.
yeah.
And
So you can do like
call
or
other circuits.
or gets A equals A, B equals B. Like for this one, I think we do and A equals A, B equals cell, out equals A cell. Oh no!
I'm trying to fix it.
I think it.
Well, we got Ryan Murphy there.
Yeah. Yeah, and then
I will
yeah.
work in Haskell for now because
Yeah.
I don't know anything about
Yeah.
this, and so
Yeah.
I'm guess I will be lost in this one.
Cool.
But in the Haskell one, I will
Cool.
continue.
And there's, if you do want to try this later, there's a hardware simulator that runs with Drum, and you can load these in and test them out. So, yep.
I'm kind of confused about the truth table on the right.
Yeah.
Because there are 3 operands, so there actually should be 8 cases in my perception.
So there would be, but this is sort of like the condensed. So,
Display them.
Yeah.
Yeah, it makes sense.
What way condensed?
so this one would have 0, 1, 0, 0, 0, 1, but those are all going to be the same. So that, and same thing for this one, it would be 0, 1, 1, right?
Okay.
So it should make it hopefully just like a little bit easier to parse. So one thing maybe to think about is that we've got the most basic building blocks that we have to solve this problem are the AND, the OR, and the exclusive OR, right? And so when you're solving these logic problems, when you use, if you're using AND, then you can check the AND for the negation, right? So if I want to return 1, I can say return 1 and not, so let me see, let's go this one. So here I could say return 1 if and not A, not B, not C, right? And here I could say return 1 if and A and not B and not C. And then, now that I'm checking on 2 of those, I can use like an OR, right? And so when you're checking for the absence, AND is a good one. And when you're checking for the presence of multiple things, even if they started out as absences, OR is a good option. And then exclusive OR is what you're looking for when only the middle case is true, right? And I think maybe the other thing that can help is to solve this, to divide this up into 2 problems. So solve first for the sum and then solve for the carry, right? And so, in Haskell, you can do that by just saying like, I'm going to solve for the sum and I'm just going to, like you can just return arbitrarily low or high for the second one while you're testing out your logic for the first one. And same thing over here. Yes, you can.
Yeah.
You can indeed.
Why complicate things?
Yeah. Remember, every time you build a circuit, you're allowed to use it in the next problem. So the half adder itself may come in handy, right? Potentially.
So it's either the carry, so it's two adders. Carry is for up left.
And if this is going pretty well for you, the bonus points is to go ahead and do a monoid instance for half adder and monoid instance for full adder. Since these are both, they're both addition. It's a little bit different than the base 10 addition that we do pretty normally, but it's still associative, and there's still an identity here, right, for both of these. And so,
Question.
Yep.
We're currently doing this manually, this HDL translation. Is this something where you would then use something like Flash and generate VDL or something like that, or is this something that you already do in this project somewhere?
So in terms of actually getting this like synthesized, yeah. So this one stops at just running. This is the first stage of the NAND to Tetris course. And so they stop at just running them through the hardware simulator. But I've looked into a couple of projects. I think it would be super cool to take the stuff that I did and actually like get it on a computer.
Yeah, because this is
But
like Flash, like
yeah.
precisely that.
Yeah. So I think that you can. One thing that the hardware simulator has the way that it works is it looks for the chip in the same directory as the chip that you've loaded. And then if it doesn't find it, it tries to use a built-in chip. And so if the tests fail for these, only if you have undefined chips inside the same directory, because it has all these chips built into it. And so if you do want to like experiment further, but you don't necessarily want to do all the tedious typing with HDL, you can just delete the empty files and then use the built-in chips. It's kind of a little sneaky. That's the monadic party inside tip, number one. Oh, it just timed out. Yeah. We're all good? Should we? Okay. Uh-huh.
Question about
Mm-hmm.
are we supposed to add two 16-bit numbers?
Yes.
Okay, okay.
And for both the increment 16 and 16-bit adder, basically, if we're just overflowing the, yeah.
Doesn't matter.
I'm not too sure about the voltage 16.
Sure.
So I managed to get my half adder and my full adder. And then
Let me see.
they kind of, yeah, that might not be the.
Okay, so for add 16, what you can do is before the equals sign, you're going to take two voltage 16s, and this is going to be kind of a lot of typing, so get ready to copy and paste. But if you put voltage 16 and then like A, B, C, D, E, F, G, H,
Hang on, so voltage 16.
and then just like 16 variables. Um,
16. 1, 2, 3, 4, 5, 6.
and maybe, yeah.
Is that right?
Maybe like A1, A2 is easier.
Yeah. Yeah.
Yeah, this is like,
I really should have zero indexed this and then start again.
and then just surround that with parentheses. Even the inside the first parenthesis is going to be right before the V in the constructor. Just right before the V in voltage 16. So it just has to destructure the whole constructor.
Okay.
And then if you copy that whole thing and then paste it again, and then do like a find and replace for A's and B's so that the variables have different names. Like, yeah, yeah. So now, after that, you put, and for me what I did is I actually put these, so this is going to be, delete that equals, and then I just put these on different lines. No, nothing, just enter. And I put, yeah, I think that they do have to line up. And then if you put equals after that one, now you can return a new voltage 16.
Okay.
And you've got what you need, right?
So what is the voltage 16?
So what the half adder does is it adds two single bits together. And so in order to do anything meaningful, we're going to need 16 bits.
Okay.
And so this is just
high-lows, 16 high-lows.
Yep.
Okay.
Yep.
Cool.
And that's how we're going to, because we're going to have, everything's going to be built on 16, like the RAM is all built upon these 16-bit words. And so those are going to be memory addresses with 16 bits of.
So if I went back to the Boolean.
Maybe? Yeah. Yeah.
It's like right now there are only exercises.
There is going to be another like small presentation.
But after the break, probably.
After the break, yeah.
Yeah, so I can unlike you because
Yep.
it doesn't make sense to.
Totally. Okie dokie. Okay, so we've got now our half adder, our full adder, and our incrementer. So this is the incrementer is simply a full adder that instead of taking two, or it's a 16-bit adder, but instead of taking two 16 bits, it just takes one and then supplies 1 as the second argument.
But can you do it in HDL?
You can send true or false to the 16-bit bus and construct your own. Yeah, it's a lot of typing, unfortunately, but okay. So the keystone for our work here, the final of the combinatory circuits, is the arithmetic logic unit. And so the goal of this, it's a single combinatory logic chip that can perform all arithmetic computation possibilities. And so this is like the same way the NAND chip was at a very small level, something that we could use to compose all of the Boolean logic and then the adding. The ALU is what we need to do subtraction, division, multiplication, and all these other things. And so the question is, how do we do subtraction with what we have, right? We've only done addition so far. And this is pretty mind-bendy for me, but it was pretty fun. And so there's a principle called the 2's complement principle. And what this says is that negative x can be computed by doing 2 to the n minus x, where x is a positive integer and n is the total binary bits available. So we're going to do an exercise for this. So in a 5-bit binary system, n would be 5. 2 would be 0, 0, 0, 1, 0. And so the reason for this is that we have 0 in the first digit, and so this is going to be 0 times 1 to the 2, 2 to the 1, 1 to the 2, 0 to the 2. And then the next one is going to be 2. And so that went forward too far. So if we do our little function, we get 2 to the 5 minus 2 is 30. And then in binary, that would be 1, 1, 1, 1, 0. And if we add these two together, it ends up with 5 zeros and then a final 1 in the 6th place, right? But since we're in a 5-bit system, that 1 is lost. And so when we add these together, if we're in a 16-bit system, it'll be the same way. So we'll always add to 16 zeros and a 1 that we lose. And so using this, we can have a pretty clever way of doing subtraction with what we have, because we know how to do a not 16, right? The not 16 will negate flip bits, and we know how to add. And so with those two things and a couple shortcuts, we can get to a pretty good spot. So, so this system has some pretty cool things. You can code a total of 2 to the n signed numbers. So the max number is 2 to the n minus 1, and the min number is negative 2 to n minus 1. And as an interesting thing, all the positive numbers will always have 0 in the most significant bit. The negative numbers will have 1. And there's this even cooler trick, which is to get negative x from x, one can leave all the trailing zeros, keep the least significant 1 bit intact, and then flip the remaining bits. And so we'll walk through this. So this would be 1, right? And so there's no trailing zeros, so we keep the 1, and then we flip the other bits, and we get 1, 1, 1, 1, 1. And if we add these together, it will, the 1 and 1 will produce a 0 with a carry, right? And then that 1 and 1 will produce a 0 with a carry, and then that 1 and 1 will produce a 0 with a carry, and then that 1 and 1 will produce a 0 with the carry, which will carry over into the 5th bit, which we lose, and so we have all zeros. If we try with 6, we have 0, 1, 1, 0. So we keep the trailing 0. We go all the way to the first 1, and we keep those. We flip the other ones, and we get 1, 0, 1, 0. And same thing here. If we add 0 and 0, we get 0. Then in the next place, if we add 1 and 1, we get 0 and carry the 1. And then we have 1 and 1, we get 0 and carry the 1. We have 1 and 1, we have 0, carry the 1, and lose the bit. And so it's kind of a a pretty cool little thing. And there's one final shortcut, which is you can actually just flip all the bits and then add 1. And that's actually how we're going to end up doing it, because it's just a bit easier to model. Because we already know how to flip all the bits. That's a not 16. And we have the increment by increment 1 for 16. That's what I have to do. So if we try the same thing with 6, we just flip the bits. We get 1, 0, 0, 1. And then if we add 1, we get 1, 0, 1, 0. And if we look at our result from before, it's the same, right? So that's 2's complemented principle. And we've already implemented the bit flipping gates. We've already implemented increment by 1. And so we've solved negative numbers and subtraction. And of course, with addition, we can accomplish multiplication. And with subtraction, we can accomplish division. And so we're ready to do the Alu Spec. So this is going to be the most complicated in terms of inputs and outputs. And I'll be around to help, and we'll just see where we get here. But we've got a single control bit F, then we've got 2 16-bit buses, an X and a Y, and then we've got 6. Sorry, that control bit was intended to be at the bottom together with the other 6. So I've got the control bits in the Haskell as a tuple with 6 items. And the way these work is that ZX stands for 0x. And so if ZX comes in as high, then we 0 the x, no matter what. And then NX is negate the x. And so if NX comes in, then we flip all the bits of the x. And then we have the same thing for y. So ZY, if that's high, then we turn all of the y's into zeros. And if we get ny, this is negate y. And so if we get that, then we will flip all the bits. So if we have a 16-bit y that comes in, right, and they're all low, and zy is high, and ny is high, what will y be? So 16 low bits coming in from y, and zy is high and ny is high. What will we get? Yes. 16 ones. Because first, the zeros or the lows will all be flipped. So first, when it comes in, no matter what, they'll be zeroed. So it doesn't even matter what comes in. It could be all zeros already. It could be 1. It could be 16. It could be anything. And so they're zeroed. And then since they're negated, every single bit is flipped. So they're all high, 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 high. And so this final control bit, no, is it actually negates the output. So if that one, so if zy is high and ny is high and no is high, then it'll zero them all, so they'll all be low. Then it'll flip them, so they'll all be high. And then it'll flip them again, so they'll all be low. And if it comes in, if we have, let's do just like a 2-bit binary example. So if we have 0 and 1, if zy is low and ny is high, then 0, 1 will be flipped. So it'll turn into 1, 0, and then it'll go out. And then if the output is negated as well, it'll be 0 and 1. So this final control bit that got moved to the top is the F bit. And if the F bit is true, if it's high voltage, then the function that will be computed on the x and the y's is addition. And if the F bit is false or low, the function that will be computed is AND. Okay? So the way to solve this problem first is to deal with capturing the result of the x after it is capture the result of the x after you take into account if it needs to be zeroed from x and then negated and flipped. So then you store that value, right? Then you do the same thing with y. You find out, and you store that value in a separate wire in HDL or in a separate variable in a let or where in Haskell, right? So then you are going to need a way to do an if, right, on the function. So what chip do we use? What chip is a good choice when we need to do an if? Not flip-flop. Mux. Mux is great, right? And so we can use the F as the selector, and we can pipe the output to an AND if it is false, and to an addition if it's true. Then we capture that output, and then you only need to deal with the final negation of the O. And so then if the output needs to be negated, you flip it one last time, and if not, you pipe it out. There is two more things that need to be taken into account, which is ZR and NG. And these are control bits that go out, that later on are used by the CPU to decide about what the following instruction will need to be when instructions need to change order depending upon what the calculation was. ZR, you will return high if the output is 0. So if everyone is low, then you'll send high out through ZR. NG is what you will send out if the output is a negative number. And so if you remember from 2's complement, there's a trick. So checking for all low should be not too bad. And then you can look at the most significant bit, because we know from 2's complement that the most significant bit will be 1 if it's negative and 0 if it's positive. All right? And so my recommendation, which is how this is structured in the course as well, is, and I gave 2 type signatures in the exercise. And actually, if you can pull from master, I added just some very naive tests, because this one can be pretty hard to kind of visualize maybe exactly what's supposed to be going on. So I added some tests to say, does 1 + 1 work? Does 2 - 1 work? And it checks these things. But what I recommend is that you actually implement it first so that it returns only the voltage, only the 16-bit voltage. And then once you have that solved, figuring out how to deal with the ZR and the NG should be much easier. But, and do it however you want, but that worked out pretty well for me. So here's the final rules. 0x input if zx, negate x input if nx, 0y input if zy, negate the y input with ny, concatenate with add if f, concatenate with and if not f, and negate the final output if no. Here is the truth table. It was too big for me to write a table in the slide. So I really recommend, and looking at it is pretty overwhelming, right? But if you go about solving it the way that I talked earlier, where you say, hey, just deal with the situation of zx and figure out, capture that in a variable or in a wire in HDL. You're good. Then deal with nx, capture it. You're good. Then do the y's, right? Add in your mux and pipe that out to and it's doable. I think what I'll do, so that's going to be our goal. So let's get to it. I will put, I'm going to start writing these rules on the board, and then I'll put the truth table back on. But I think the rules are probably more helpful in this case. And the rules kind of do the job of figuring out what the truth table means for you. Yeah.
Still having issues with generating the one constant for the increment and in the HDL version, which is just an adder.
Let me see.
The simple question is, how do I just create?
Yeah, so I think that you have to do it, the syntax requires you to do it inline in the B. Let me look up the syntax real quick.
Inline in the B.
But you can say 0 to 6, I think you can say, there's a shorthand for it, so let me look it up. So you can access it with bracket notation. So you got it. So you can say B1 ... 15 equals false, just straight in the, and you can actually give multiple ones as well. So you can say.
Currently got this version which doesn't parse.
So,
it's down here.
False has to be lowercase.
Oh, damn it. Okay, and true the same.
Yep. Yeah, that's right though.
Okay. Nice, thanks.